So the first thing we need to do is actually learn how to write our hypotheses. And before I jump into that, I just want to do a review over here on our symbols. So repeating the inferential process that we did in the last chapter, we're going to be using sample statistics as our best point estimates for our parameters. So that was when we were looking at creating confidence intervals. And now the process will be testing claims made about parameters. So we're going to start with testing claims that people make about a population mean. To evaluate that claim, we would rely on a study that takes sample data. So we would rely on X bar to help us make a conclusion about a statement concerning the population. All right, I'm going to come down to proportion next. So lowercase p, population proportion, and we used p hat, the sample proportion, as our sample statistic to determine a conclusion about our population. All right, and then symbols here. So population standard deviation, the sample statistic is S, sample standard deviation, and variance, population variance sigma squared, sample variance S squared. So just a review of the symbols that we've been using. All right, and then we're ready to write our hypotheses. So the null hypothesis, H subscript 0, the alternative hypothesis, H subscript 1. Just going to make a note here, the alternative hypothesis, also called the research hypothesis, some books will write it H subscript A for alternative. Either one is totally correct. We tend to use this one though. So H1 for alternative. All right, so here's the way it works. The null hypothesis is going to be a statement of equality, like dogs treated with DAP pays the same amount as placebo-treated dogs. So kind of a statement of no change. Something will be equal to a value. The alternative hypothesis is always a statement of some kind of change. So we're either going to see symbols like less, like dogs pays less, or greater, or possibly not equal to. So those are the only symbols that we are allowed to see when we look at our alternative. Now, before I go on here, I'm going to come back to null hypothesis. So you'll hear me say H naught. So instead of saying H subscript 0 or null hypothesis, it's also read H naught. So that word not, N-A-U-G-H-T, it's kind of like the English version of 0. So not, you can just think of another word as another word for 0. So H naught. Okay, so let's start to talk about writing the hypotheses, and I'll talk about this part once we get into an example. So it says for each conjecture, we're going to state the hypotheses. We're going to identify a claim that's being made and indicate the direction of the hypothesis test. And we'll talk about direction here in a moment. So let's jump into a claim being made. So in hypothesis testing, a claim will be stated. And in this case, a legislator claims that more than 75% of constituents favor her proposal for funding a new city dog park. All right, so I'm going to come over here to my hypotheses. So H naught, H1, and they're followed by colons. And we are always going to start with writing our claim, because our claim will be our research hypothesis. So the claim here is that the percentage of people that favor the funding is more than 75%. So this is representing a proportion, so a percentage, a proportion. So I'm going to do P here. So she says that among all of her constituents, she thinks that the true proportion is more than 75%, and write that in decimal. She thinks that more than 75% of her constituents favor her dog park proposal. All right, so if we were to take a sample and this claim was true, then we would expect our sample proportion to be significantly bigger than this. So if she says that the proportion is bigger, my sample proportion when she collects her data, so there's your p hat, I expect p hat to be significantly greater. So we say significantly because we really want to be convinced this is true. So if she went out and got data and her p hat was 76%, that might not be enough to convince me that everybody, all of her constituents, the percentage is greater. So we really look for numbers that are significantly bigger than this, and we'll sort of define significantly as we go. But right now, again, just kind of getting a general idea. So this is what she's hoping to see if she does her study and her claim is true. The null hypothesis is always a statement of equality. So the proportion, and it's always an equal. So we start off with the proportion is 0.75. It's up to the legislator to go get some data and convince us that it's the claim that's true. So that's how hypothesis testing works. We're going to assume the proportion is 0.75, 75%. Then we're going to go get some data and see if we get a number significantly bigger than this so that we're convinced that she is correct, or he, whoever this person is, this legislator is correct, that the proportion is bigger. So if we want p hat to be bigger than 75%, we're looking for numbers to the right of 75% on a number line. So if you think of a number line, numbers bigger than this are to the right of it. So we call this a right tail test. Now, when I wrote up here, I wrote symbols for the mean, but it applies to proportions or any other population parameter. So when we have a greater here, it's called a right tail test. So we're looking for evidence of a number on a number line further to the right than that. So we call it a right tail test. Okay, so let's try this again. Right, so a manufacturer claims, we always look for this claim, they claim the mean, so now we're looking at mu, the mean time to complete the assembly of a certain toy is less than 10 minutes. So we're always going to start with writing our claim, and our claim, I'm just going to write C in parentheses for claim. Our claim is our alternative hypothesis. So now it's a mu for mean, and they think that for all people that try to assemble this toy, that on average, that mean they think it's under 10 minutes, at least that's what they're claiming. So the null hypothesis, H naught, it's always the same symbol for their mu, it's always equal, and then it's always that same number that was in the claim. So the way it works is we're going to say the mean is 10 minutes, and they're going to have to get some data for us to convince us that the mean is really under 10 minutes. So if they take a sample and the claim is true, then the sample mean, then we expect X bar, we should be getting something significantly smaller than 10 if you want to convince me the true mean is smaller than 10. So again, if you think of a number line, numbers smaller than 10 would be numbers to the left of 10, and that's why we call this a left tail test. So hopefully it's going to be a very logical process. I'm going to do a little highlighting here. If the claim is that a parameter is bigger than a number, it's a right tail test. If the claim is that a parameter is less than a number, then that's a left tail test. All right, one other possibility. So let's do the third one here. All right, so now it says the mean height of a certain type of plant is 30 centimeters. A researcher speculates that the mean height differs for plants exposed to a certain pesticide. All right, it doesn't say the word claim, but it does say speculates. So I like when we just say the word claim to make it really obvious, but there can be other English involved. So in this case, speculates, but we'll still identify that here as the claim that's being tested, or the speculation. And this is mean, so mu. All right, and they say that they think the mean is different from 30 centimeters for these plants exposed to a pesticide. So it's not as strong as saying they think the mean is taller or they think the mean is smaller, shorter. They just don't think it's going to be 30. They think it's going to be different. So this is when we just say we don't think it's equal to, so not equal to. So we think plants exposed to the pesticide have a mean not equal to 30 centimeters. So if we went out and did a study and took a sample of plants exposed to the pesticide, then that sample mean, I would expect it to be significantly different. So maybe it'll be much smaller than 30, or maybe it will be much bigger than 30. Either way, it would convince me that the mean is not 30. So this is called a two-tail test because numbers to the far right of 30, or maybe to the far left of 30, either way, I would be convinced the mean is not 30. So this is called a two-tail test. And the null hypothesis always is equal to that number stated in the plan. Okay, so our claim will be our H1. I don't ask you to say the other one's not the claim because it's not, so we don't have to write both. We're just identifying here the claim being made. And we will always be doing problems where our claim, our research hypothesis is our H1. All right, so let's just do a few more here. All right, so a researcher claims that less than 40% of people exercise every day. So if they're giving me a percentage, that again is a proportion. So let's write that claim. So our claim is that the proportion of people who exercise every day, and I wish they said that, the word proportion here, a researcher claims that the proportion of people who exercise every day is less than 40%. But it's just a little bit more streamlined. It doesn't say the word proportion, but it's a percent. So we know it's a proportion of people, and they think it's less than 40%. So if they think it's smaller than 40%, then we expect our study to result in sample proportions to the left of 40%. So numbers smaller than 40% are to its left. That's why it's called a left tail test. And we'll be drawing graphs of all this shortly. Again, just trying to get the idea here. The null hypothesis, always equal and always the same number that was in the claim. So as we read longer questions, it's really just good to focus on the claim because there will be more numbers involved in problems once we get moving. All right. Last year, 38% of school children in a particular state received reduced price lunches. A researcher claims that this proportion has changed. All right, so our claim now, they say proportion, so now it's easy to recognize P there, population proportion. They think it's changed. So they don't say they think it's higher. They don't say they think it's lower. They just think it's not what it was before. So this is our not equal to. So they don't think it's 38%, 0.38 anymore. And that's what makes this a two-tail test. So not equal to is two-tail, and then the null hypothesis, again, always an equal and the same number from the claim. All right, last one. The mean height of a certain type of plant is 30 centimeters. A researcher believes that the mean height is greater for plants grown with a particular nutrient supplement. All right, so now our claim, we're talking about means, mean height. They think that, they claim that the mean height will be greater than 30 centimeters for plants that get a nutrient supplement. So if I do a study, I would expect my sample mean to be greater than 30, significantly bigger than 30. So if I want to be convinced this is true, I'll be looking for numbers to the right of it on a number line. So numbers bigger than 30 are to the right of it. So we call that a right tail test. And then the null hypothesis is the equal 30. So before I leave this page, I'm just going to highlight some words here. So I'm just going to go back to the top. As we're reading sentences and looking for keywords, the first one was talking about more than 75%. More than is a greater than. The second one said less than 10. Less than 10 minutes is a less than sign. And then the third one talked about heights differing. So differs, and that's our not equal to. So there's going to be keywords that tell you what symbol to put in your H1, your alternative hypothesis, and therefore know if it's going to be a left tail test, right tail test, or two tail test. So I'll just highlight the remaining ones here. So less than 40% is a less than sign. Has changed is a not equal to, not the same as, so it's different. And then that last one was is greater, and that's why it's greater. All right, so that is the first step. Can you read a conjecture, a statement here, and write the two hypotheses?